Is my screen visible?
Yeah, it is.
Yeah. So today's paper presentation is on incorporating BERT into neural machine translation. And so basically in NMT, we use neural network models to learn a statistical model for machine translation. And neural networks like MLP were used earlier, but we got major improvements with RNNs in the encoder-decoder architecture. So basically, the encoder is built by stacking RNN layers. Like this is the encoder. So these are basically RNN layers. And the output of the encoder is basically a hidden state. And this is also the last time step of the last RNN. Now the output is basically a 2D vector that encapsulates the whole meaning of the sentence, whatever the RNN was able to get from this sentence. And it tries to store that information in this, represent that information in this. And the role of the decoder is to convert this vector into an output, like which would basically mean something in like, let's say English, like whatever the target language is for translation. And it is built with RNN layers and a dense layer to predict the English word. And in basically the decoder for each time step, the RNN can receive either the same hidden vector for all the layers, or it can receive the output of the last last layer. Now, this is a very basic model which we can improve by adding attention mechanism. So basically, there was a glaring problem with the previous model that all the input sentence meaning is captured in one single vector, right? Now, so as the length of the sentence will increase, it gets more difficult for the model to capture the information in this vector. So as the sentences get longer, the performance decreased and the vector itself became a bottleneck. Now, with this new structure, we're keeping all the hidden states for every time step of the encoder. And we're basically, so now the hidden vector is a matrix basically, and made of all the hidden vectors from the time steps. Now, this solves the problem of having enough having like not enough information with just one vector, but it adds the exact opposite problem, which is too much information. Now the attention mechanism is used to solve this, and it can be applied only once. And it is the piece that connects the encoder and the decoder. Now we'll visit the encoder, the attention mechanism and exactly how it works, the math behind it later. And the problem with this model is that the RNN works sequentially. That means that in order to compute the second word of the sentence, we need the first hidden vector to be calculated, the first time step. Then in order to calculate the hidden state at time t, you always need results from t-1. So we cannot parallelize. Also, RNN with attention has improved the understanding of how one part of a sentence can affect it later, but it still struggles with longer sequences. So we haven't completely solved the problem. Now, coming to transformers, we basically removed the RNNs from the models and self-attention mechanism was used. So basically the encoding component is a stack of encoders. So basically there are multiple such encoder layers in the encoder model. And these encoders share the same structure. Like these all have self-attention and they have a feed-forward neural network layer. Now, each encoder is composed of two layers, as I mentioned, but we can apply this as many times as we need, as you want to. The decoder has the same architecture, but it also has an encoder-decoder attention layer. We can think of this as the attention layer we saw between the encoder and decoder in RNNs with attention. So we can think of this in the same way. So now that we have the architecture, basically, so let's look at how it works. We basically begin by turning the input into, we get the embeddings from the input using some sort of embedding algorithm. And the embeddings are only fed to the bottommost encoder layer. Now, all encoders receive a vector of the same size. And for the bottommost, that's obviously embeddings. And for others, it's the output of the encoder below. And the word in each position flows through its own path in the encoder. So basically, estoy will flow through one, de will flow through one, and so on. And so basically, for the feed forward part of the layer, all words can go through it independently, and thus you can parallelize it. There is some dependency involved in the self-attention layer. But yeah, like we can parallelize because in the feed forward layer, all three can have their own separate paths. So now we come to like exactly how self-attention works. Now, the first step is basically to create three vectors: the queries, keys, and values. Now, these are created by multiplying the embeddings by the we multiply the embeddings for each word by three matrices that we train during the training process. So these matrices are called WQ, WK, and WV1. We multiply those with the embeddings to get Q1, K1, V1, and so on for each word. And then okay. And then in the second step, we calculate a score. And this score is, so let's say we're calculating the self-attention for the word thinking. We need to score each word of the input sentence against this word. The score determines how much focus to place on other parts of the input sentence as we encode a certain position. So for thinking, the score, it would have multiple scores. So Q1, K1, Q1, K2, and so on for all the rest of the words in the input. And basically, the score is calculated by taking the dot product. And if you're processing the self-attention for the word in position number 1, and the first score would be the dot product of Q1 and K1. And basically, it's kind of obvious how basically the score for the word itself would be the highest, but it also makes sense to look at other words which would also have a big impact on how to interpret a certain word. Like, for example, the word it is probably referring to something else in the sentence. So that you get a high score for that as well. So the third and fourth steps are to divide the scores by the square root of the dimension of the key vectors. So basically, we divide this by the dimension of K1. And basically, then we put this through softmax to normalize the scores and make sure they add up to 1. And the softmax score determines how much each word will be expressed at this position. And then we come to the fifth step, which is multiplying each value vector by we multiply each value vector by the softmax score to get one sec. Yeah, and so we multiply the softmax vector with the softmax scores with the value vector, and then we sum up and then we sum up all the different softmax all these vectors to get a final representation Z1, and this is for every single word. And instead of the vector the dot products which we've used for vectors, we can actually do this for entire matrices by combining like making a matrix out of each and every word, combining together. And basically, multi-head attention is a module that runs for attention mechanisms, which runs through an attention mechanism several times in parallel. Now, the independent attention outputs are then concatenated in some way and linearly transformed into the expected dimension. That is different from self-attention, which we've seen here. This is basically how it works. Input, the embedded get X. Now, that's only for the bottommost layer. Here we have, for every other layer, it's the input from the layer below. We have matrices trained for 3 matrices trained during the training process. We use these, multiply them with the embeddings, get the Q, K, V, We concatenate them, as we saw in the process earlier, to create Z0, Z1 up to the entire length of the matrix. And then we multiply these with the weight of the matrix W0 to produce the output layer Z. Also, so to take into account the positioning of the words in the initial sentence, the transformer adds a vector to each input embedding. Now, the intuition is here. The intuition is that adding these values to the embeddings can basically provide meaningful distances between the embedding vectors once they're projected into QKV vectors and during the dot product in the attention. And so yeah, so basically we have the embeddings, position encoding, and you get the embedding which we'll actually input to the rest of the process. Now, so as you can see, this is encoder layer 1, encoder layer 2, and so on. And so yeah, we've discussed self-attention, and we also need to use layer normalization after each sub-layer in the encoder. And so like after self-attention, we use a normalization layer, feed forward, and then normalization layer, and so on. The self-attention layers in the decoder operate in a slightly different way. In the decoder, the self-attention is only allowed to attend to positions earlier than the word width thinking. So if the input is, let's say, A, B, C, and we're currently at B, then you can only look at A and not C, something that happens later. And this is done by masking future positions before the softmax step in the self-attention calculation. In the encoder decoder attention layer, it basically works just like multi-headed self-attention, except it creates queries matrix from the layer below it, and it takes the values matrix from the output of the encoder stack. So queries is from the layer below it, and values and keys from the ones which it gets from the encoder stack. So basically, BERT functions exactly like the transformer is described. But what makes it so special? Now, directional models have been used to read text input, but they do it sequentially, which is either left to right or right to left. And the transformer is able to read the entire sequence of words at once. So people call it bidirectional, but it would be more accurate to call it non-directional. And this allows the model to learn the context of a word based on all of its surroundings. Now, the way we train this is by making it solve two problems. The first is that basically 15% of the words in the sentence are masked, and BERT tries to predict these masked words. And the second one is that basically the model receives pairs of sentences as input, and the model tries to predict whether the second sentence is a subsequent sentence or a consecutive sentence, or is it just some random sentence in the input? So in coming to this paper, and what they exactly did was, the model for NMT is called the BERT fused model, in which the output from feeding the text into BERT, so they basically fed the text into BERT, and the output, which is shown by HB here, is fed into the NMT model. And it's fed into all layers rather than just the input layer, which was done in previous works. And compared to standard NMT, there are two extra attention modules. So instead of just having a self-attention here, we actually have the BERT encoded attention also. And similarly for the decoder, we have the BERT decoder attention also. And so basically an input sequence is first transformed into representations. And then by the BERT encoder attention module, each NMT encoder layer interacts with these representations obtained from BERT, and eventually basically gets output from both of these attention mechanisms, and it tries to fuse them together. And we'll see exactly how it does that. And yeah, so the decoder works in a similar way as the encoder. And again, it tries to fuse the output of these two. They also experimented with two other approaches, and their blue scores were compared with the BERT fused model. And so one of the approaches was initializing the NMT model with pre-trained BERT, And in the second approach, they simply used the embeddings from BERT and input them to the classical the RNN and MT model. So in the BERT fused model approach shown in the figure, step one is basically inputting the given sentence. The capital HB represents the BERT representation, and this small HB comma I, which we see later on here, basically HIL. So basically this represents the embedding of the nth layer ith word, and the representation we get out, the hidden representation we get out of it. And capital HEL denotes the hidden representation of the nth layer. And so that's it. And so in this first equation, we see how the first attention term is basically from the S denotes the self-attention model, and the second is the BERT attention model. And this basically is how the NMT model combines the input from these two attention mechanisms. And as we can see, it's basically some sort of arithmetic mean of the two. And this continues for every single encoder layer till we get the final encoder output. And in the second equation, the capital SLT denotes the hidden state of the nth layer in the decoder. And basically in the decoder, the output from the self-attention layer is fed to both the BERT decoder as well as the encoder-decoder architecture model, as we can see here. And the final attention output is again taken by calculating the arithmetic mean. And then after this, we have the feed-forward network, feed-forward neural network, and then layer normalization is applied. And this takes place in every decoder layer. And in the end, we end up with the output vector, which represents the translation. Basically, it's a vector which we can map to in a dictionary, and that gives us the exact translation. So the third equation is used to calculate the attention in terms of the attention that we see in these equations is calculated like this. And this is basically the what we've discussed earlier, but they've just done it in matrix form, and that's why it looks like this. And the fourth equation represents the feed-forward neural network, and W1, W2, B1, B2 are all parameters that need to be learned. And so in this paper, similar to the dropout technique we used in deep learning, etc., they've used dropnet technique, which is again for the same purpose, regularization. And it ensures that the features output by BERT and the conventional encoder are fully utilized. So both these equations are very similar to those discussed earlier. For example, like in this, we are again calculating the small HIL that we had previously used. This is the hidden state for the ith word in the nth layer. So basically, big U here we see is a randomly sampled variable for each iteration, and it's in the range of 0 to 1. So for every iteration of training, we sample a variable from 0 to 1, and that's our U. And peanut is a set dropnet rate, similar to the dropout rate we have in deep learning. And I represents the indicative function. So basically, based on every iteration and the different U and peanut values, one of these three terms is actually non-zero. One of these terms is non-zero. And for any layer with probability peanut by 2, either only the BERT encoder is used, or only the self-attention is used. But for probability 1 minus peanut, we use both the attention models to get the embeddings. And during inference time, the expected output of each attention model is exactly the equation we discussed earlier. And it turns out to be this. And similarly, the same thought process is carried out for this, for the decoder. And yeah, and these are the results of the study. So this is a standard transformer. These are the blue scores. So this is the standard transformer. So this is the BERT fused transformer they've used. And basically they've tried to experiment removing certain parts. So here they are like changing certain parts of the experiment to see how it affects the blue score. So here they've randomly initialized the encoder decoder of the BERT fused model. They've jointly tuned both the BERT and the encoder decoder structure, and so on. Yeah. And they've tried removing certain parts to see how that affects, etc. And this is basically the training curves for different p-net values. So I like to think of it exactly as I think of dropout rates, because in essence, it tries to serve the same purpose, which is prevent overfitting. And so, yeah, they've mapped the blue scores to different p-net values. And a key future research direction that they offered in the paper is to compress the BERT fused model into a light version. Basically, what they're proposing is using knowledge distillation to combine pre-trained models with NMT. And yeah, that's all from my side. Any questions?